Welcome to the lecture series of 12th Standard Physics. And the first topic in this lecture series, as you all can see, is rotational dynamics. So, the first topic that we are going to start in rotational dynamics is nothing but rotational motion. So there is a basic definition. The spinning motion of a body about an axis passing through it. About an axis passing through it is called as rotational motion. Now, let's see with a few examples. So, if I have a sphere, let's say I have a sphere like this, and this is an axis that is passing through the sphere. So, when the sphere starts to rotate about this axis as shown in the figure, the spinning motion of that sphere is called as rotational motion. Is called as rotational motion. So, the axis for rotational motion has to pass through the body. If the axis is lying outside the body, we won't be able to call it rotational motion. So for example, let's say if I have a cylinder, let's draw a cylinder. So I have a cylinder over here, and let's say I'm drawing an axis like this, and this is the axis. So about this axis, the motion is called as rotational motion. But if in both the cases, let's say I'm drawing an axis, which is out of the body. So in both the cases, there will be rotational axis about this axis 1, about the axis 2, but about axis 3 and 4, there will be no rotational motion. So no rotational motion about axis 3 and 4. And the reason behind this is since they lie outside the body. So whenever we are defining rotational motion, we need to remember that it is a spinning motion, and for spinning motion we need to define an axis, and in case of rotational motion, that axis must be passing through the body. If the axis is lying outside the body, then the motion of the body is not rotational motion. Okay. The next topic is relation between rotational motion and circular motion. So for this case, let us consider a sphere. So I have a sphere like this, and I'll draw an axis. This is the axis of the sphere, and the sphere is rotating about this axis. Now, if I mark a point on the surface of the sphere, that point will be seen performing circular motion in this direction if the sphere performs rotational motion. So we can write a relation between circular motion and rotational motion using this example, and that relation is as follows. First, I'll quote it, that whenever a body performs rotational motion, then the points on the body will perform the circular motion. Okay, so when a body performs rotational motion, the points on it perform circular motion. Okay, good. Okay, now the next topic that we are going to see is the relation between linear kinematical equations and rotational kinematical equations. So first, let's write down linear kinematical equations. Linear kinematical equations. Now, we have three kinematical equations. The first is V is equal to U plus AT. Second, S is equal to UT plus half AT square. Third, V square is equal to U square plus 2AS, where T is time, V is final velocity, U is initial velocity, S is displacement, and A is acceleration. Now, if we want to write down rotational kinematical equations, we just need to remember a few replacements, and the replacements are as follows. So in linear motion we have S as the displacement. In the rotational motion we have theta as the displacement, and it is called as angular displacement. Angular displacement. It is measured in radians. Then, instead of initial velocity, we have omega naught, which is initial angular velocity. It is measured in radian per second. In place of final velocity, we have omega, that is final angular velocity. The unit is same. And in place of acceleration, A, we have alpha, that is angular acceleration. And its unit is radian per second square. Radian per second square. Now, using these replacements, we can easily write down the relations, kinematical equations. First, omega is equal to omega naught plus alpha t. Second, theta is equal to omega naught into t plus half alpha t square. Third, omega square is equal to omega naught square plus 2 alpha theta. So, using linear kinematical equations and certain replacements which I have shown on the page, we can easily create rotational kinematical equations. Okay, let's discuss angular velocity in a little bit detail. Angular velocity. Now, as we have seen, the symbol is omega, and velocity is a vector, therefore we must put a bar. Angular velocity omega bar. So the first thing is definition, and definition is angular velocity is nothing but rate of change of angular displacement. Rate of change of angular displacement. And therefore we can write down omega is equal to d theta by dt. D theta by dt. Now, second, it's a vector quantity. Therefore, we should be able to find out its direction. We should be able to find out the direction of the omega bar. Now, before finding the direction of omega bar, the first thing that we need to know that it is an axial vector. It is an axial vector, which means that it will always be along the axis of rotation. It will always be along the axis of rotation of the body. Now, let us consider an example of a disk. So let's draw a disk. So this is a disk. We have a disk over here, and let's draw the axis of the disk. So this is the axis of the disk. Now, let us consider that the disk is rotating in anti-clockwise direction. In this case, if we are observing from the top, and if we see that the body is rotating in anti-clockwise direction, then the rule to plot omega is that if the body is rotating in anti-clockwise direction and we are observing from the top, then it is towards us. The omega bar vector is towards us. Therefore, if we are observing from the top, and if the body is rotating in anti-clockwise direction, then omega bar should not be towards us, it should be away from us. So in the second case, when it is rotating in clockwise direction, we are observing from the top, then omega bar vector should be away from us. Okay, so let's summarize this point. So if we observe the body to be rotating in anti-clockwise direction, then omega bar is towards us. But if we observe the body to be rotating in clockwise direction, then omega bar is away from us. And in both the cases, I have depicted diagrammatically the direction of omega bar when the body is rotating in clockwise direction and when the body is rotating in anti-clockwise direction. Okay. The next topic that we are going to see is relation between V bar and omega bar. So V bar is tangential velocity, omega bar is angular velocity, and R bar is radius vector. r bar is radius vector. So first I'm going to give you the vector relation, and the vector relation is as follows. V bar is equal to omega bar cross r bar. And if we just need the magnitude, we can write down V is equal to r omega. So these are the two relations that you need to remember. The first is the vector relation. V bar is equal to omega bar and r bar, omega bar cross r bar, and the magnitude relation V is equal to r omega. So there are simple examples on this in CET as well as in boards. Let's see one example. Let's say that the omega bar vector is given to be I cap minus 2j cap plus 3k cap. And the r bar vector is given to be I cap plus j cap plus k cap. And they've asked us to find out V bar. So we all know V bar is omega bar cross r bar. Then we'll have to solve the determinant over here. I cap, j cap, k cap. First, the coefficients of the vector omega bar 1, minus 2, 3, and then 1, 1, 1. So finally, the answer comes out to be I cap multiplied by minus 2, minus 3, minus j cap multiplied by 1, minus 3, and plus k cap multiplied by 1 plus 2. So the answer comes out to be minus 5 I cap plus 2 j cap plus 3 k cap. And this is what I think is the answer for tangential velocity V bar. So this is the simple questions that they ask. So the two relations that you need to remember is V bar is equal to omega bar cross r bar, and V is equal to r omega. Okay. So moving on to the last topic of this video, it is nothing but relation between time period, frequency, angular frequency or angular velocity omega. So we have to deduce the relation between these three quantities. Now, we all know that t, which is nothing but time period, is time taken by particle to go once around the circle. Once around the circle. And that we all know is nothing but the circumference divided by the speed. The circumference divided by the speed. But we just saw that V is nothing but r omega. R and R gets cancelled. So we get this relation, that is T is equal to 2 pi by omega. T is equal to 2 pi by omega. So this is the relation between time period and angular velocity omega. Now, we all know time period is 1 over frequency. And using the above relation, 1 over f is nothing but 2 pi over omega. And we get a relation between omega and frequency, that is omega is equal to 2 pi f. So these are the other two relations that you need to remember. Okay, fine. So this was the first lecture for rotational dynamics. In the next lecture, we will be covering the topics of uniform and non-uniform circular motion. And in the later lectures, we'll move on towards the derivations, which are asked in the board examinations, like banking, angle of banking, maximum speed limits, etc. Thank you.